This slide shows the definition of AI given by William Webster, where he intends to state that AI is defined as the capability of a machine to imitate intelligent human behavior. It means whenever a machine applies human behavior intelligently, it is termed as artificial intelligence. In this slide, we learn more definitions of AI, wherein the first one is AI is the theory and development of a computer system to be able to perform tasks normally requiring human intelligence, such as visual perception, speech recognition, decision making, and translation between languages. So, if tasks like these are accomplished with the help of a computer system or machine, we say that we have used artificial intelligence. The second definition is artificial intelligence is a way of making a computer controlled robot, or a software think intelligently in the comparable manner the intelligent humans think. Clearly, if a machine is able to employ human behavior intelligently, we say that that particular machine is powered by AI. Third one is AI is accomplished by studying how human brain thinks and how humans learn, decide and work while trying to solve a problem, and then using the outcomes of this study as a basis of developing intelligent software and systems. So, the efficient deployment of AI in a machine requires to understand how human behavior works at solving a problem. If the machine can understand how human behavior works, it is said to be artificially intelligent. In this slide, we shall discuss some applications of AI. From Siri to self-driving cars, AI is progressing rapidly. While science fiction often portrays AI as robots with human-like characteristics, AI can encompass anything from Google search algorithms to IBM's Watson to an autonomous weapons. So the first point is an example of a few areas where AI use is increasing. Siri from Apple, Google Assistant from Alphabet, Cortana from Microsoft, and Alexa from Amazon are currently ready to assist you with more and more difficult tasks. So these are the virtual assistants powered by AI, especially the chatbots that I told you about in the first module. Then artificial intelligence, machine learning, deep learning are just the beginning of a revolution that will transform everyday life and how we interact with technology. So these technologies are now required in the market very dearly, and investing in learning and using these technologies is indeed proving very helpful to many already. More details about what exactly machine learning and deep learning are and how they are related with AI will be discussed in further topics. So this slide is about the Turing test. It is named after a famous computer scientist and mathematician Alan Turing. The Turing test considers the following setting. There are two rooms A and B. One of the rooms contains a computer and the other contains a human. The interrogator is outside both the rooms and does not know which one is computer, and he can ask questions through a teletype and receive answers from both A and B. The interrogator needs to identify which one is human out of A and B. To pass the Turing test, the machine has to fool the interrogator into believing that it is human. So if a machine passes the Turing test, it is clearly said to employ artificial intelligence. Now we shall learn what are agents and environments. An agent is the actual program that carries on the task of AI, and an environment is the universe in which the agent operates. An agent perceives its environment through sensors. The complete set of inputs given at a time is called a percept. The current percept or a sequence of percepts may influence the actions of an agent. So what it is saying is an agent receives input through sensors from the environment, where each set of inputs is known as a percept, and the current percept or a sequence of percepts may decide what the agent's output shall be. Here, output of agent is also termed action. Each action is implemented by actuators which are invoked according to the AI program flow. An agent can change the environment through actuators. An operation involving an actuator is called an action, and actions can be grouped into action sequences. So agent is a system or a program or a computer or a machine or a robot to which we are planning to provide AI capability. An agent acts in an environment, as we have discussed earlier. The agent can have goals which it tries to achieve. Here, goals are output requirements from the agent that can be a set of actions to be performed or the outcome of those actions. A performance measure has to be used in order to evaluate an agent. The performance measure is a subjective measure to characterize how successful an agent is. So how we measure performance of an agent? The success can be measured in various ways. It can be measured in terms of speed or efficiency of the agent. It can be measured by the accuracy or the quality of the solutions achieved by the agent, and it can also be measured by power usage, money, etc. So an autonomous agent decides autonomously which action to take in the current action to maximize progress towards its goal. So for autonomous agent, no user intervention is required while the agent is working. Next, we see various types of environments where an agent is deployed. First is fully observable versus partially observable. So if it is possible to determine the complete state of the environment at each point of time from the percepts an agent gets, it is observable. Otherwise, the environment is partially observable. Here, state of the environment means its attributes, and if those attributes are getting determined by the agent, then the environment is fully observable, else partially observable. Second one is deterministic versus stochastic or non-deterministic, which states that if the next state of the environment is completely determined by the current state and the actions of the agent, then the environment is deterministic, otherwise it is non-deterministic. Here, deterministic simply means that each attribute change of the environment is solely dependent on the action of the agent, and non-deterministic means that the environment does not depend on the actions of the agent alone and can change on other factors. I will take an example here. Suppose you are employing AI to power a search algorithm, then the next states of the search from its current one depend on the set of actions the search agent takes to go from current state to the next. But on the other hand, if you are powering a vacuum cleaner with AI, the complete environment can change outside the control of that particular vacuum cleaner, and the amount of dust can vary from various other factors. So the first example was that of deterministic environment, and the second example was for stochastic environment. Next we see episodic versus sequential or non-episodic, which states that in an episodic environment, each episode consists of the agent perceiving and then acting. The quality of its action depends just on the episode itself. Subsequent episodes do not depend on the actions in the previous episodes. But episodic environments are much simpler because the agent does not need to think ahead. Such is not the case in non-episodic environment. So what this means is, suppose we deploy AI in a system which requires learning on behalf of the agent. Learning implies that agent stores a set of percepts and actions that have been done and applies some logic based on them to the current percept so as to better the goal. This is termed as sequential or non-episodic, wherein actions for every episode is done sequentially from past episodes. The episodic case is vice versa, where the agent simply acts on the current percept regardless of past experiences. Next, we have static versus dynamic environments. If the environment does not change while an agent is acting, then it is static, otherwise it is dynamic. Then we have discrete versus continuous environments. If there are a limited number of distinct, clearly defined states of the environment is discrete. For example, a game of chess, where every state is distinct from other one, and there are finite state of states that can be in a game of chess. So otherwise it is continuous. For example, driving, where there can be many undefined states for the environment. Finally, we have the single versus multiple agents, wherein the environment may contain other agents which may be of the same or different kind as that of the agent, in which case it is multiple agents environment, else it is a single agent environment. For designing an AI agent, the following measures are taken into account. which is the P's description of agents. P for performance measures, which evaluates how well the agent solves the task at hand. E for environment, which implies surroundings beyond the control of the agent. A for actuators, which determine the actions the agent can perform. And S for sensors, which provides information about the current state of the environment. Next, we see the page description of an AI and ML model, where P stands for percepts, which are information acquired through the agent sensory system. A stands for actions, which are operations performed by the agent on the environment through its actuators. G stands for goals, which is the desired outcome of the task with a measurable performance. And E stands for environment, which are the surroundings beyond the control of the agent. So in this slide, we see the piece description of a vacuum cleaner with AI. Suppose you are using an artificially intelligent vacuum cleaner that is supposed to clean the house on its own, that is, without human intervention. So what would be the piece description for that machine? Let us see. So performance measures for that vacuum cleaner will be cleanliness of the floor, time needed and energy consumed by the vacuum cleaner. Environment will be grid of tiles, dirt on the tiles, possible obstacles and varying amount of dirt on the tiles, etc. Actuators shall be movement, which are wheels, tracks, legs and so on of the vacuum cleaner, and dirt removal of by the nozzle gripper and so on. So the wheel, tracks and legs and so on are the actuators, and the action performed by them is the movement. And similarly, nozzle, gripple, etc. are the actuators used for the action of dirt removal. So next will be sensors for detecting the environment. In this case, it shall be position sensors, dirtiness sensors, which shall be sensing the amount of dirt on the surface, and possible movement sensor that shall determine if it is possible to move from X to Y, which are camera and wheel movement sensors, etc. In this slide, we look at a popular problem solving technique, which is searching. A search problem is defined in terms of states, operators, and goals. A state is a complete description of the world for the purposes of problem solving, where initial state is the state the world is in when problem solving begins, and goal state is the state in which the problem is solved. An operator is an action that transforms one state of the world into another state, and goal states are the end goal output or number of output required by the program. Depending on the number of solutions a problem has, there may be a single goal or many goals. For example, in the 8 queens puzzle, there is a single solution and a single goal state. I'll be discussing what an 8 queen problem is later. In chess, there are many winning positions and hence many goal states. Now I'll be explaining more about operators. In general, operators can be applied to only select states and not all the states. For example, in a game of chess, a particular move is determined by the rules of chess for that particular piece in the current state. For instance, you must have heard about the 8 queen puzzle configuration, where it is required to put 8 queen pieces on a chessboard so that no queen attacks each other, and the target goal is to find such an arrangement of 8 queens on the board. In such a scenario, the next states after the current state in the search process are limited, as the current queen cancels out its row, column and the two diagonals that it sits on. So only some moves are physically possible for the next queen. So finally, the set of operators which are applicable in a state determine the state that can be reached from S. In this slide, we'll be learning states and nodes and what they are. A state is a representation of a physical configuration, which implies that a state can be a real world entity of the problem of search. For example, in the Hamiltonian path problem, what is the state in that? A state is a current vertex that has been traversed from previous vertices or a set of vertices. So nodes in the search tree are data structures maintained by a search procedure representing paths to a particular state. This implies that nodes are data structures maintained by the search procedure which represent path to particular state. So for in the Hamiltonian path problem, as I have mentioned, what the nodes will be, it will be data structures containing the set of vertices that have been traversed before that current vertex. So the same state can appear in several nodes if there is more than one path to that state. I hope this is clear. In the Hamiltonian path problem, for example, one vertex can be reached by several routes, so there can be several nodes in the search tree for that particular state. The path can be reconstructed by following edges back to the root of the tree. So if we traverse back to the root of the tree, we'll obtain the path to that state or particular current state. Now I will discuss some more points about searching as a problem solving technique. Searching is the process of finding the required states or nodes, which are the end goal of the program. Searching is to be performed through state space, which is the set of states that are valid for the current and upcoming states. Search process is carried on by constructing a search tree. So this search tree is based on different operators resulting in different leaves of the tree and can be made in a breadth first or a depth first way. Search is a universal problem solving technique. Search involves systematic trial and error exploration of alternative solutions. Many problems don't have a simple algorithmic solution. Casting these problems as search problems is often the easiest way of solving them. Examples are finding a complete cycle in an undirected graph for which no known complete algorithm exists yet, which is also known as the Hamiltonian path problem. So it is useful when the sequence of actions to solve a problem is not known. For example, as I have told, pathfinding problems or 8 queens puzzle, traveling salesman problem, etc., or two-player games such as chess and checkers. Now we shall discuss the problem of searching, or more precisely the algorithm of searching. The algorithm to do a simple search is shown in these steps here. First, we check whether the current state is a goal state or not. It implies that if it is indeed the goal, then we show the state spaces used to reach this goal as output and exit the algorithm. Or otherwise, we move on to the second point, which is expand the current state to generate the new set of states, which implies that we apply applicable operators and determine the set of states that can be reached by applying those operators and save them in a data structure. And then we move on to the third point, which is choose one of the new states generated for search depending on search strategy. So this can be done randomly or based on some priority set by the user. Next, we repeat steps 1 to 3 until the goal state is reached or there are no more states to be expanded. So the above algorithm will result in the goal getting obtained or not depending on the problem instance. So what are search strategies? A search strategy is defined by picking up the order of node expansion and the strategies are evaluated along the following dimensions. Completeness. Does it generate to find a solution if there is any? It means that whether the search strategy is chosen such that the states obtained at each step result in the solution finally or not. Optimality. Does it always find the highest quality or least cost solution? So, does the search strategy implies that we get the least cost solution or not? For example, in the traveling salesman problem, we need to find the complete cycle of cities traversed by the salesman that has the least distance covered. Time complexity. How long does it take to find a solution? This implies the time factor of the search. Space complexity. How much memory does it need to perform the complete search? This implies how much computer resources the search employs. Time and space complexity are measured in terms of first is B, maximum branching factor of the search tree, and this is the basically breadth of the search tree, and D, depth of the least cost solution, And finally M, maximum depth of the state space, which may be infinity as well. Types of search. Uninformed or blind search. It involves search where there are no criteria of selecting next set of states from the current state, and all the possible other states must be selected to achieve the target goal. Second one is informed or heuristic search. Informed search tries to reduce the amount of search that must be done by making intelligent choices for the nodes that are selected for expansion. This implies the existence of some way of evaluating the likelihood that a given node is the solution path. In general, this is done using a heuristic function. So in this slide, we'll be learning constraint satisfaction problems. Many problems in AI can be considered as problems of constraint satisfaction in which the goal state satisfies a given set of constraints. Constraint satisfaction can be solved by using any of the search strategies, but we do need to apply the constraints at every search instance so that the new search state space is correct. So what are constraints? This implies a set of rules so to reach the next state from the current state. So in this slide you see general form of a CSP or constraint satisfaction problem. So until a complete solution is found or until all paths have led to dead ends, perform the following steps. Select an expanded node of the search graph. Apply the constraint interference rules to the selected node to generate all possible new constraints. So we have to apply all the constraint rules to the selected node. So we get the unobvious nodes out of the search. Then, if the set of constraints contains a valid contradiction, then report that the path is a dead end. So it implies that there is a contradiction, or we have reached in fact a dead end. Then we report that, and otherwise, if the set of constraints describes a complete solution, then report success. So if these constraints describe a complete solution, then we report success to the output. If neither a constraint nor a complete solution is found, then apply the rules to generate new partial solutions. Insert these partial solutions into the search graph. Repeat the above steps again. So this is the way to go about the constraint satisfaction problem. In fact, we can apply any of the search strategies before, but we do have to apply all the constraint rules at every step. Now we will discuss a very interesting problem of CSP problem, which is Sudoku. You all must be knowing Sudoku, in which there are blocks of numbers, and there are precisely 9 blocks, and each block can contain numbers 1 through 9, and every row must contain all the numbers 1 to 9, and every column should also contain the number 1 to 9, and no block is to repeat any number. Similarly is the case with row and columns. So this is a problem of CSP where given a set of numbers and a set of empty spaces in a Sudoku, which is a Sudoku problem instance, we have to fill the Sudoku so that it is valid, and at every such instance of solving that Sudoku puzzle, we have to apply the constraints which I have just mentioned. So what it says is, at each empty cell we can fill the remaining numbers from the block provided that the number is unique in its row, that the number is unique in its column, and the number is 1 from 1 to 9.